This is lecture number 26 of the course AU 203 Statistics and Quality Control. In this lecture, we will talk about start with the classification in statistics, what we call it an inferential statistics. Then we will go into point estimation and then we will go into differentiating between what is point estimate and what is point estimator. And then we will look into unbiased estimators, definition of unbiased estimators, and then we will look into the properties of good estimators. Unbiased estimator is one of its property. And then we will look graphically the relationship between the bias and the variability. So broadly speaking, when you talk about statistics, you can divide into two halves. One is called descriptive statistics, other is called inferential statistics. So we already have seen in descriptive statistics, we are dealing with mean, some measures of central tendency and measure of the dispersion. So you analyze the data, you visualize the data graphically. So all this come into the branch of statistics, what you call it a descriptive statistics. Whereas in inferential statistics, you are dealing with the parameters, and usually parameters means any quantity of interest which is you are required to predict or you need to test. Or you need to make decisions about any quantity of interest from a population, when this is what you call it parameters. So obviously these parameters, the value of those parameters are always unknown, and what we need is to take a sample from that population, and we came up with statistics, and these statistics are always from a sample, and from the basis of those samples you make decision about the parameters which is from population. So we will look into that, and so we can say there are different types of tests and predictions associated with inferential statistics, in which we are required to make decisions and make predictions. One of them is called parameter estimation, and parameter estimation is further divided into two parts called point estimation and interval estimation. So today's topic is point estimation. We will deal it in detail. And in the later lectures, we will go into the second type of second branch of inferential statistics, what we call it hypothesis testing. Let's say we have population. Population doesn't mean people, as I've already explained several times, and the size of the population is represented by capital N, and its central tendency is represented by mu, and sigma is showing its standard deviation. So this is something population. So once we study this whole population, so if you know the total number, you can calculate particular characteristic related with that population. So you calculate different probabilities, and this type of study in which you have some larger set of information available, or you could have a general theory, and you make deductions to come up with particular information. That reasoning is called as deductive reasoning. So deductive reasoning means the specific information about sample can be deduced from a larger from a general theory. If you make deductions from a general theory to reach to a specific conclusion, that reasoning is called as deductive reasoning. Whereas the second type of reasoning, what you call it in inductive reasoning, means you have information, specific information available, which is only good for a smaller case, what you call it a sample, and from that you make an inductive reasoning to predict the behavior of a general theory. This is called as inductive reasoning. Probably you have already done at your first year mathematics level called mathematical induction, in which you have to prove something, a general result from some basic result, like you put some n equals to 1 or n equal to 2, n equal to 3 and n equal to k, then you can generalize it to a general theory that the sequence is valid for a general case as well. So that is actually called as inductive reasoning. So once you are dealing with population, it means you are actually dealing with the parameter, the characteristics of the population are represented, what you call it, a parameters. So parameters are always taken from a population, while once you are dealing with the samples, so you come up with the quantities of interest, what you call it, statistics. So statistics is always taken from the samples. So in inferential statistics, what you do is you predict the behavior of the population using a sample. So from specific information, what you get it from the sample, you predict a general theory about, or you predict something about a population. So that is what the subject of inferential statistics is all about. Whether it is a point estimation or whether it is an interval estimation. Okay, now once you will go into the theory, then you will better understand. Okay, so there is a term called estimators. So if you recall, in your childhood, probably you have played that game dodgeball. So what is actually your target is, the eye hole is your target, and you want that all of your strikes go directly to the target, but it never happens. So some targets are away from the eye and some are close to the eye, and you always looking for some parameter of interest, which is in this case is a bull's eye, which is a center point where you want to hit all the time. But what could be the possible cases is, for example, if let's say this first case in which the target is at the center, but most of your attempts are away from the center, and we have seen that most of them are below the center line, or it could be opposite, most of them you're far away from the center, but they are above the center line or bullseye. Or a third possibility could be your attempts are not at the target, but several on the above the center and several below the center. So it means your estimation about how well you put your target, there are different possibilities. So once you are experienced, then most of the things would be close to the center. So that is something what is actually intended. So all the time this would be your best marksmanship. It means you are trying to mark at the center. So this would be something in ideal case. So what is an estimator? We can call an estimator is a rule or a strategy which is usually expressed by some mathematical formula that actually gives us information about how to calculate an estimate. And this estimate is based on the information given in the sample. So estimator can be thought of as a rule or a strategy which is expressed in the form of a formula, and that gives information about that actually help us to calculate an estimate. So estimator is one thing, estimate is another thing, and that is something, the values you got from your samples are your estimates. So for example, for a population mean, which is a parameter, and a sample mean is a statistic, and so we can call it a sample mean, which you are getting it from the information you are getting it from a sample, and that estimator, this formula, this rule that whatever your values of x, you take the sum and divide by the number of trials, you are going to get the sample mean. So sample mean becomes a strategy or a formula. Then this sample mean, which is always you taken it from your sample in order to predict the behavior of your population, that is called as an estimator. The sample mean would be an estimator. Okay, what you call it a point estimation. Point estimation refers to providing a single best guess of some quantity of interest. So it means you are only interested in the point data. You are not interested in the interval data. So you are not interested in the range. You are interested in a particular value associated with the quantity of interest. And in statistical inference or predictions, the quantity of interest could be parameters, because you have certain population and you are interested in predicting the behavior of the population from a parameters, and this parameters could be a mean, standard deviation, it could be a population proportion. So all your parametric statistics is dealing with the parameters, which are always about some population. Or you could have some obviously all these PDFs and CDFs are actually can be a quantity of your interest. So you are interested in finding out the overall behavior of x, and that gives you that function f of small f of x gives you the probability, and capital F of x is actually giving you the cumulative density function, which we already have explained it earlier. Or it could be a prediction for some future response value based on some variables. For example, y equals to 2x plus 1. So x is, let's say, your random variable, and that depends on the value of y depends on the value of x. So once you are interested in your quantity of interest could be the response y. So that is based on a random variable x, for example. So any quantity of interest could be you are interested in, but you are interested in its single value or say best value, so that you can show you can characterize its behavior. Okay, now the term called point estimator. So point estimator is always an statistic, and a statistics is always come from a sample. But this is statistics is predicting something, a behavior about a parameter, and we already know that we use Greek letter to represent parameters like mu and sigma, or in general we call it theta. So theta is a Greek letter which is actually the characteristic of a population. And what is point estimator? Point estimator, we use capital theta and having a cap on it. So that is actually an statistic. So that is always from a sample. So this estimate is actually helps you to predict something about your population. So this would be capital theta cap would be called as a point estimator, because you are interested in a point value or a single value. You are not interested in the range of the values. In interval estimates, you will be dealing with the range of the values rather than a one particular value. Okay, in this today's lecture, we will be only talking about point estimate. So the value of that point estimator is represented by small theta, but since it's an estimate, it is a particular value of that. That would be represented by small theta with a cap on it. So without a cap, it is a parameter, and with the cap, it would be the value of the statistic. And statistic is a capital theta with a cap, and here, since it's a single numerical value, we call that statistics to be a point estimator. So take an example. For example, if we have 100 observation, and a sample mean is computed. Let's say your sample mean, the value of your sample mean is 86.4. So here your sample mean is your estimator, and this estimator is statistics. So for example, sample mean is statistics from the sample, so that's why we call it estimator. And theta cap, what you call it, is actually the value of that sample mean. So we usually represent small x to represent the value of the sample mean. So for example, in this case 86.4 is actually the value of a sample mean, which is an estimator, which is predicting certain population. So that's why we call 86.4 as a point estimate, whereas the sample mean is a formula or a general rule, what you call it, that is sample mean is a point estimator, and the value of the point estimator is called point estimate. So this is the difference between point estimator and point estimate. For example, we have a population parameters. So always we use a Greek letter to represent a population parameter. So mu, variance, sigma square, or p is representing the mean, variance, and proportions. And the formula to predict this population parameter is called a statistic, and that statistics is represented by certain formula. Here sample mean would be estimator, or variance of a sample would be an estimator, or population proportion, and we use a cap on that p to represent an estimator, because in general we have a Greek letter, or it could be an estimator could be represented by a capital Greek letter, whereas small Greek letters are used for population parameter. Estimator is always about sample. Population parameter is about population, and the value we compute from that formula sigma x over n, the value is called as an estimate. And estimate is always from some estimator. So sample mean is an estimator, whereas the value of the sample mean is called an estimate. So better to understand the differentiation between estimate and estimator. In general, if x is a random variable, and the probability of any value of the random variable is represented by f of x, which is actually predicting some unknown parameter from a population, which is represented by theta. Let's say your x1, x2 be your random sample of size n from the population x, which is and the statistics theta cap would be some function of the random variables x1, x2, and xn. So it's not all x1, it's an x1, x2, xn. Will be called as the point estimator of that parameter theta. So whenever you talk about estimators, we always put a cap on that. So that would be your point estimate, and the value is called point estimate, and the formula or the mathematical function would be called as a point estimator. So point estimator is a general rule or a strategy which is used from the sample to predict the population. So that's why it is called as a point estimator. And we must understand that this point estimator itself would be a random variable, because it is a function of random variables x1, x2, and x3. And once you take a sample, you calculate some of the values called estimates, point estimates. And so these we represent by small theta with cap on it, called the point estimate of a parameter theta. So this theta is a general name. It's theta could be mu, theta could be sigma square, or theta could be a population proportion. and theta cap would be the value of those estimators. And estimators are the mathematical functions or the formula which allows you to calculate some quantity of interest from your sample in order to predict the behavior of the population. So the value of the point estimate, since it is depending upon the random variables, so these values are going to change from sample to sample. So this itself would be called as a random variable, and we will see it once we will go on to Minitab. Then we will see how if you take a sample from a population, a fixed population, so every time you come up with different statistics. For each sample, you would have different estimate of the value. Okay, so here at this point, I could see that your point estimators, which are frequently used in engineering, would be a single best estimate about your prediction about your population from a sample. Mu would be it could be one of the parameters. Variance could be one of the parameters, or proportion could be your some formula to calculate the proportion would be your point estimators, or the difference of the two means would be your estimators, or the difference in the population proportion would be your estimators, whereas the particular value coming for that estimator would be called as we call it to be the estimates of those estimators. So these are all your values. For example, in order to predict the population parameter mu, the point estimator is a sample mean, and we can use to, even if you put a theta cap, which would be the particular value of the point estimator. So here calculating the mean is just a formula, what you call it a point estimator, whereas the particular formula is an estimator and its value is called estimate. So whenever you talk about estimate, you could even you use a Greek letter, but you put a cap on it, that would be representing the estimate. And estimate is the value of the estimator. Estimator is some formula which you employ for your sample in order to predict population parameters. So these are all corresponding value of the estimators. These would be called as point estimates. Okay, then the question comes about biased and unbiased estimator. So when your estimator or a single guess value is representing the true value of the population, and in all the cases we know that the population parameters are unknown, so we don't have information about the population parameters. So if you satisfy the definition that all your point estimators, it means capital theta cap, these are always from a sample, would be an unbiased estimator for the parameter theta if the expected value of that point estimator is equal to the parameter. So then it would be called as an unbiased estimator. So this is by definition. We could have different estimators. Mean is one estimator, variance is another estimator, sample mean, sample variance, and sample proportion. These are all the estimators. If their expected value is the same as the population parameter, then it would be called as an unbiased estimator. So for example, if this condition is not satisfied, then such an estimator would be called as an biased estimator. If it is not unbiased, it means it would be called as a biased estimator. So one can think of, let's say, if the true value of the population is this, and your distribution also predicts the expected value or the of the distribution is the same as the mean value, then it would be called as an unbiased estimator. If the mean value is different and the population mean is different, then it would be called as not satisfying this condition, that is actually called as a biased estimator. And how much is the difference between the expected value of the point estimator with this parameter is called as the bias of an estimator. So once this bias is equal to 0, it means you end up with this condition, then your estimator would be called as unbiased estimator. Otherwise, it would be called as biased estimator. We already have seen this definition for unbiased estimator is if you have a estimator which is always from some sample, and if you calculate the expected value and you end up with the value would be the same as the population parameter, then this parameter theta cap would be called as an unbiased estimator. And we have already seen in the sampling distribution case, your sample mean, once you calculate its expected value, it will be equal to the population mean. Then we can say that this parameter sample mean is actually an unbiased estimator. So let's say if you have this population represented by X and this population parameter is mu, which is something about the population. And if you take samples, let's say for 4 sample size, and you calculate an sample is a point estimator, a sample mean is a point estimator, and if the expected value of the point estimator is same as the true value of the population parameter, where here we are talking about mean, then it means this estimator X bar, which is some formula, would be called as unbiased estimator. And we have already seen that as the number of samples are increasing, the variance becomes smaller, and this fact is so the sample mean becomes the unbiased estimator of the population mean. Let's say we have to prove here that S square is an unbiased estimator of the parameter population parameter sigma square. So mathematically what you need is expected value of your estimator would be, if it is the same as the population variance, then we can say that this estimator would be called as unbiased estimator. So definition of sample variance is, we already know that each observation, if you make a difference with the mean value and take the square and divide it by n minus 1, since n minus 1 is because we are dealing with the sample. So estimator is always from a sample. So here that's why you have n minus 1 sample size is there, and once you put an n here, then it would be called as sigma square, which is about population. Here estimator is always from a sample, so that's why we use this definition for S square. Okay, the next thing is to calculate the expected value of S square. So expected value of S square would be this, and then they're all mathematics based on the rules of expectations. We have already learned that 1 upon n minus 1 is a coefficient we can take out of that expected values. Expected value of this sum of this difference and its square would be remain, and then we know that x minus x bar is a formula a square minus 2ab plus b square, and then this term in the bracket can be evaluated because as you know, x bar is no more changing with the index I. So take out of that summation notation, and then we need to simplify it. We know the definition for x bar is some estimator, which is some rule or a formula that all the values of x to be summed up together and divided by the sample size in order to get this. So this is the definition for the sample mean. If n is multiplied by the sample mean, then nx bar would be sum of x. So sum of x can be represented as n times x bar. So n times x bar, and x bar would be x bar square. Similarly, we can write down this thing would be sum of x bar square. So if you take the sum to all the values from 1 to n, then it would be n times of x bar square. Okay, now just to do the simplification work, minus 2n x bar square plus n x bar square would be minus n x bar square, and then you use the properties of expected value. That expected value of sum of x square would be actually expected value of x square, and then take the summation. You can use this rules for expected value. We have already defined it earlier. So using that, if you simplify further, here, as you know, expected value of x square is linked with the variance of x. So you know that expected variance of x would be the expected value of the x square minus the mean whole square. So that is the definition, and we know the x is your random variable, and so it is about sigma square, and that is mu square. So you can write expected value of x square would be equal to mu square plus sigma square. So instead of expected value of x square, you can write similarly, if you're dealing with sample mean, which is x bar, so variance of x bar would be expected value of x bar squared, because you are dealing with expected value of x square and expected value of x bar squared. So the definition for x bar square is variance for the sample. We already have seen it. Sampling distribution would be equal to sigma square over n. And this thing is the same, and expected value is same as the true mean value, because here x bar is your unbiased estimator. Then this two expressions for expected value of x square, which is this, and expected value of x bar square is known, substituted back into that equation, and then you just need to simplify it, and what you end up with is, after simplification, that expected value of x minus x bar is n minus 1 times sigma square, and if you substitute the expected value of s square formula, then the whole thing in this would be n minus 1 into sigma square. So n minus 1 cancels out, so you got the expected value of this point estimator is equal to the population variance. Then we can prove that the sample variance is actually satisfying this definition for unbiased estimator. Then your sample variance is an unbiased estimator. This is what we have proved in this formula. But keep in mind, expected value of S is not the same as sigma. So even though the variance is an unbiased estimator, but standard deviation is not an unbiased estimator. Okay, so one of the property of a good estimator is that it must be unbiased. So there are three properties associated with a good estimator. First one we have already addressed, unbiasedness. Unbiasedness means an expected value of the estimator, which always comes from a sample, would be equal to the true value of the population parameter, which always come from the population. Parameters always comes from the population. So the first property, once it is satisfied, then it would be a good estimator. Second property is called consistency. The third property is called minimum variance. So we look at one by one. Consistency means, for example, we have already seen in a sampling distribution, if the sample variance we calculate for a sample, what we see is, once your number of sample size increases, then your variance is decreasing. It means once n is very large, then it would be called as your estimate is improved one, then we call to be consistent. So once you have an estimator which is having this feature, this property called consistency, then it would be this the second property associated with the good estimator. Okay, the third property is called is, because if you have an estimator which is satisfying the first two properties like unbiasedness and consistency, but next third thing you need to look into the minimum variance property. So if we consider all possible unbiased estimators of some parameter theta, then one with the smallest variance would be called as the most efficient estimator, or sometimes we call it a minimum variance estimator. MVE represents a minimum variance estimator. So you have once you have a large variance, then dispersion is more. Once you have a smaller variance, it means it is a minimum variance estimator. So if we compared with two estimators, the estimator which brings smaller variance would be the better one. So these, if we have to look about any which one is the good estimators, then we need to look into these three different properties: unbiasedness, consistency, and minimum variance. Okay, here you have a sampling distribution of three different estimators. So theta 1 cap, theta 2 cap, and theta 3 cap of same population parameter theta. So these are, you can think of different samples, sample statistics, which are your estimators taken from the same population, and the parameter of the population is theta. So if theta 1 cap, if its expected value, which is highest frequency here, so the first part is which of the estimator is the biased one. So if you see unbiased theta 1 have the same mean, which is the population mean, then we or population parameter, if it is the same, then we call it to be unbiased. So here the both dash ones are actually your this theta, and if you look at this theta 2, which is the dashed one, but its expected value is also the same as, so it means theta 1 and theta 2 both are unbiased estimators. So it means the expected value of theta 3 is different from the population parameter, then this estimator theta 3 is actually a biased estimator. Theta 1 and theta 2 would be called as an unbiased estimator. Okay, the next thing is which of the estimator is the most efficient unbiased estimator. So you have three estimators, whereas the theta 3 is doesn't satisfy the first condition of unbiased estimator. So we get rid of them. Now we need to look into between theta 1 and theta 2. So we look into theta, the second property, consistency. So both theta 1 and theta 2 are satisfying consistency, in the sense that if the sample size is increasing, then the dispersion is decreasing. But as you see, compared with theta 1 and theta 2, theta 1 has some smaller variance than theta 2. So that is actually satisfying the third condition, minimum variance estimator. So that's why theta 1 would be the most efficient estimator, because it satisfies all three conditions. And theta 2 also satisfied two conditions, but compared with theta 2 and theta 1 has minimum variance, whereas theta 2 has more variance. So that's why theta 1 is the good estimator, or the best estimator here, or the most efficient estimator here. Okay, estimators could be anything. I mean, let's say, for example, we have a sample of 4 observations, and from this unknown population with the mean mu and variance sigma square, and we take x1, x2, x3, 4 samples, which are representing some, which are the random variables, because x1 can take any value, x2 can take any value. So let's say we have 2 estimators, which are from your sample x bar and x star. So definition or a formula or a strategy for x bar is take the sum and divide by 4. Whereas x star is x1 plus twice of x2 plus twice of x3 plus x4 and divide by 6. So this is the formula we have worked out for an estimator x star, which is different from x bar. So these two formulas are representing, they are the point estimators. So now what we look into this problem here is which of those estimator, X bar or X star, which one is the most efficient estimator. So we need to look into the properties of the efficient estimator. So the first property is if you calculate its expected value for both X bar and X star, you end up with the same population mean, then it means it is unbiased. Both are unbiased estimator. Then obviously we can look at the consistency, which would be true, but if the third parameter, then you need to look into the minimum variance estimator. So if you calculate the variance of X bar and if you calculate the variance of X star, so which one is the minimum variance? 5 upon 18 is a smaller number, or 1 by 4 is a smaller number. So we know that 1 by 4 is a smaller number than this. So this X bar becomes the most efficient estimator in this case, because it satisfies all the three conditions of efficient estimator. Let's say you have another problem in which a railway train gets late by X minutes. So X is a random variable. It could be 5 minutes, it could be 10 minutes, or 30 minutes, whatever it is. So a random sample of 50 journey gives this data that some of the time in which the train is late is 7:38, and sum of X square is this value. Calculate the unbiased estimate of the mean and variance of this population from which the 50 samples have been drawn. Okay, so this is the first part, and the second part is there 7 times the trains are late by 25 minutes. Find the unbiased estimate of the population proportion. So this is the second part. We will do it one by one. So first, dealing with the first part, let X be the number of minutes the train is late, and we calculate the expected value, so that we know that X is the expected value of X, which is a point estimator, is actually the same as the true mean. So variance is sigma square, let's say. So now we need to calculate the sample mean, and we know sum of X over n is the formula, because here the sample size is 50. So 14.6 becomes a value, or it is an estimate of an estimator. X bar is some formula which is an estimator, and the value of that estimator is called an estimate. Here 14.76 is your estimate. The next thing, you work out the unbiased estimator of the expected value is same as the population, then it would be satisfying the unbiasedness. The next, look at the unbiasedness estimate of the variance, which comes out to be 114.96. So this is what we have calculated, the unbiased estimates of the mean and the variance. In the second part, there are 7 times the trains are late by 25 minutes. So it means the proportion P is when the train is late by 25 minutes is out of 50 different samples 7 times. So it would be 0.14. And if you the unbiased estimate of the population parameter, it is also 0.14. So it is satisfying. It means that would be the unbiased estimate of this population proportion where the train is late by more than 25 minutes. So we need to look into those properties for estimators. So in this lecture we have gone into what is point estimates, what are point estimators, and what this process is point estimation called, because you are interested in the single value which is representing which is a represent from a sample predicting certain population. Okay, the last thing is relationship between bias and variability. We have seen that the definition for bias is when your expected value of your point estimators is the same as the true value of the population parameter, then the bias would be 0. Otherwise, there would be some difference between the estimator and the which is estimator is always statistics from parameter which is always from a population. For example, if this is your case in which your target is the true value is in the center, and most of your observations, your sample estimates are away from that, so which represents the data has so much bias. It means it is the true value, the estimator is not close to the true value. So, but within the observations, the variability dispersion is low. So, this observation would be called as having a high bias but low variability. Whereas if you have, this is a case in which you have very high variability because data is away from the target, as well as the observations are away from this true value, which is within, so it would be low bias. Because low bias in the sense that the expected value is this difference is a smaller number, but since within the observations within the sample there is a variability, so variability always lies within the sample, so showing high variability. But low bias in a sense that I mean this target is the bullseye, so the thing is so much so several observations, I think 1 2 3 4 are in this close to the eye, and then the next circle would have most of the eyes, so a lot of the observations are in this representing the true value, so that would be called as low bias, but the variability is quite high because within the observations there are a lot of differences, within the observations there are very less difference. Okay, it could be the situation in which the bias means not at the center, not true value of the population parameters, then the high bias, as well as the dispersion is there, so called as high variability. Or this would be an ideal case in which no bias or zero bias when you're expected, which is called as an unbiased estimator. So that would be the one of the efficient estimator, and additionally it has very low variability within the samples. The variability is very low. So this is the link between bias and variability. So for a good estimator, we need to be having three properties: unbiasedness, or bias should be zero, and consistency, and minimum variability. So if you have a minimum variability, then would be your best or the most efficient estimator. This is where I stop this lecture.